In this video, what we're going to do is we're going to talk about the relationship between solubility and solubility product. It's easy to get the two terms confused. They're not the same thing. Solubility is the amount of a solid that will dissolve into a certain amount of water. So for example, I might say that a solid, 1 gram of it dissolves into a liter of water. 1 gram per liter would be called the solubility. Or I might say that it's 0.05 moles of the substance dissolves into a liter of water. In that case, we would use moles divided by liters to talk about the solubility. The solubility product is the equilibrium constant, KSP, a unitless quantity, which in a sense reflects the solubility. So they're related, right? The amount that dissolves, the amount of a substance that will dissolve into a liter of water or 100 milliliters of water, solubility is connected to this idea of what the value of the solubility product is. The larger the value of KSP, the more soluble the substance is. The smaller the value of KSP, the lower the value, the less soluble the substance is. Okay, so let's take a look at an example. And this says we're going to use KSP to calculate the solubility of a compound. Now, keep in mind, I'll just let you know, some textbooks will use the symbol S in these sorts of calculations, and others will use an X. We're going to use an X because Alex uses an X, and that's, it's consistent with the using X as the variable or the unknown that we dealt with in acid-base chemistry. Okay. So this says calculate the solubility of COOH2, which is cobalt 2 hydroxide, in water at 25 degrees C. Remember, the temperature is important because the higher the temperature, generally solids become more soluble at higher temperature. Not all of them, but many of them do. You'll find the KSP value, the data for it in the Alex data tab. For, I already looked that up, for cobalt 2 hydroxide is 5.92 times 10 to the negative 15, okay? And then you want to round your answer to 2 significant digits, okay? Let's take a look at this one. Okay, so the first step is kind of like the first step that we did in the previous video, which is you take the solid and write out the expression, write out the equation for dissolving it into water. So hydroxide is -1, and there's 2 of them. That means that the cobalt's got to be +2. So cobalt 2. And then again, don't forget there's 2 hydroxides. And then we're going to write them as aqueous. So that's the chemical equation. The expression for KSP is products over reactants, but the reactant is a solid, so we don't include it. So concentration of cobalt times concentration of hydroxide. Again, don't forget the 2, the exponent goes in there, okay? Or the coefficient becomes an exponent. Now, what I'm going to do is I'm going to write the value. KSP is 5.92 times 10 to the -15. That's the value that I looked up on the data table, data tab for Alex for cobalt 2 hydroxide. Now, here's what we're going to do. We're going to go through the initial change in equilibrium table. So I'm going to rewrite the chemical equation so we have room for that. Okay. Now, again, this is a solid, so we don't need to worry about it. It's, no concern over solids because they're not involved in the equilibrium. Now, initially, when this goes into the water, none of it has dissolved. But over time, some of it will dissolve. So the initial concentration of cobalt is 0, and the initial concentration of hydroxide is 0. Now, technically, that's not true because water does form some hydroxide, right? 10 to the -7 molar, pH 7. So there actually is some hydroxide in the water, but what we find with these calculations is that most of the time we don't need to worry about that. Okay, we can ignore it. So we'll just have its initial as 0. then what happens is this starts to dissolve, right? It starts to form cobalt and hydroxide. So this is going to go up by X, and this is going to go up by 2X, right? Because there's 2 hydroxides. Every time that one of these is formed in the water, 2 of these are formed in the water. So once we reach equilibrium, 0 plus X is X, and 0 plus 2X is 2X. Okay. Now, remember, these are equilibrium concentrations. We can substitute them right back into that equation. And so KSP would be cobalt, which is X, hydroxide squared, which is 2X squared. Don't forget that it's 2X squared, right? The hydroxide is 2X, but we need to square the hydroxide, so we need to square the 2X. So what you get is X times 2 squared times X squared, so you get 4X cubed. And that is equal to 5.92 times 10 to the minus 15. Okay, now here's what I'm going to say. Solubility is the amount of solid that dissolves into a volume of liquid or a volume of solution, right? It's the solution, the volume of the solution. Now, one way to do that amount could be grams, or it could be moles, it could be other units as well, but the most common units are grams per liter and moles per liter. Okay, so in this particular problem, what they do is they want you to do it in grams per liter. They say calculate the solubility. They don't explicitly say to use grams per liter, but that's what they want. They want to have it in grams per liter. So just keep in mind for the Alex problem, this is what they want. Okay, now the strategy we're going to use is that, remember, this is all about molarity, right? This is all moles per liter when we do these equilibrium calculations. So what's going to happen is we're going to solve for X, and that's going to give us moles per liter for the solubility. Okay, so when you find X, that is the solubility. It's the amount of the substance that dissolves into a liter of water because of the units that we've used. So you solve for X. So let's go through here. How do we solve for X? Well, let's go through the algebra. First step, divide by 4, right? Because 4 divided by 4 is 1. Now we've got X cubed equals 5.92 times 10 to the minus 15 divided by 4. Remember, we have to divide both sides by 4. Okay, so let me just go ahead and write that out. 5.92 divided by 4 is 1.48. So this is 1.48 times 10 to the minus 15. That's equal to X cubed. So if we want to find X, what do? You take what's called the third root, right? If you had X squared and you want to find X, you take the square root. If you have X to the cubed, X to the third power, X cubed is X to the third power. You take the cube root, okay? Now, this can also be written as X to the 1/3. So the cube root is the same as 1/3, okay? So we're going to take the cube root. Now, some calculators have a cube root function. Other ones do not, but they will very often have this function where you can put in anything that you want here and it'll do that root. So if you want that to be third root, you would put 3 and then the function. If you want it to be fourth root, you would put a 4 and then you would put the radicals, okay? So what I'm going to do is I'm going to see if I get this right. 3 root 1.48 times 10 to the minus 15. Oops, and I got a little syntax error. Okay, so let me try it again. 1.48. There we go. So I've got cube root of 1.48 times 10 to the minus 15. And that's going to give me 1.14 times 10 to the minus 5. Okay, so the cube root. Now, that is actually going to be in the units of moles per liter because of the way we've defined the KSP as being concentrations in the units of moles per liter. So the only thing that we have left to do is to convert this to grams per liter. Okay, so I'm going to do that up here. So let me erase all of this just so that we have room. Okay, now what we need to know is how do we convert from moles per liter to grams per liter? I hope you remember how to do that, right? Converting from mole, the liters are going to be the same. We're converting from moles to grams. So typically what you do is you multiply by the molar mass. If you take concentration in moles per liter and multiply that by the molar mass, that will convert from moles to grams. So we need to know what the molar mass of the cobalt hydroxide is. So cobalt, let's see what the molar mass of cobalt is. I have to look that up on a periodic table. So let me bring up a little periodic table here. Handy right here. So cobalt is 58.933. Okay. So 58.933. Oxygen is 16.00, but there's two of them. And then there's two hydrogens, so 2 times 1.01. Okay, so that's what? 32, 34. So 34.02 plus 58.933. Looks like we got 92.953. That's a 9. Okay, so let's see if this works out. Here's what we have in terms of X. That's the solubility. 1.14 times 10 to the minus 5 moles per liter. Now, what I said earlier was we're going to multiply by the molar mass. So let's see if the units work out. 92.953 grams per mole, right? Those are the units of molar mass. Look what happens. The moles cancel, and you're going to get a number that's going to be in grams per liter. And that's exactly what we want for the solubility. So 1.14 times 10 to the minus 5 times 92.953, and you get 1.06 times 10 to the negative 3. Now they probably just want 2 digits. Let me come back to the question. 2 significant digits. So that doesn't mean, that's not the same as 2 decimal places. 2 decimal places would be 2 digits past the decimal point. So 2 significant digits, you would round that to 1.1 times 10 to the minus 3. And there you go. So there's your solubility in grams per liter. The ALEKS questioning problem is not explicit. And I want to point out that it's very common in most textbooks, what they have you do is calculate the molar solubility. That would just be what X is out of our, the cube root of KSP over 4. But in the ALEKS problem, they want us to do one more step, which is to find the molar solubility. So do that extra last step. Let me show you one more example. where they actually give you a few ions. Okay. Let's try this one. So calculate the solubility of Ag2CO3 in water at 25 degrees C. You'll find the KSP data in the Alex data tab. So again, we're going to find the solubility Ag2CO3. So you have to be able to figure out what this is going to break up into. So here's our metal. Now, you may or may not remember this from Chem 11. There are 3 ions in the periodic table, which are pretty cool, the pattern you get. One of them is silver. Silver is element 47. And then you have zinc, which is element 30. And then you have aluminum. Makes a little staircase over here. It's element number 13. And what happens is this one's +3. This one's +2. And this one's +1. It's a cool pattern. AZA, it's aluminum, zinc, and silver. +3, +2, +1. So that means the silver is +1. But there's 2 of them. So that means the carbonate's got to be -2. The carbonate is one we would know as a polyatomic ion. So 2 silvers and a carbonate. Okay, so let's write out the expression. I'll do it down here because the calculations will be down here. So we have silver ion squared, right? There's a 2 there, so squared times carbonate. Okay, now we have to look that value up. And looking it up, it appears as though it's 8.46 times 10 to the -12. Okay, now let's go through the little ice calculation, the little box, ice box, sometimes people call it. Again, this is a solid, so we don't need to worry about it. These are 0 before anything dissolves. After it does dissolve, this goes up by 2x, and this goes up by x, 2-to-1 ratio. So once they're in equilibrium, you've got 2x and x. So that means that our KSP is 8.46 times 10 to the -12, but it's also 2x squared. See how that shows up? The 2 shows up twice and then times x. It shows up twice because it dissolves it. 2 of them are formed, but then the way that we write equilibrium expressions is we use exponents for the coefficients. So it shows the 2 shows up twice. Okay, so this actually mathematically is just like the one we just did. It comes out to 4x cubed. Most of the problems they're giving you are 1-to-1 or 2-to-1. Okay, so we're going to solve for x again. So this number divided by 4, right? So 8.46 times 10 to the -12 divided by 4 is going to give us x cubed. And then if you take the cube root of that, that'll give you x. Okay, so let me see what 8.46 divided by 4 is 2.115. So that's the cube root of 2.115 times 10 to the -12. Okay, all right, so let's see. So 3 cube root of 2.115 times 10 to the -12, close the parentheses, and you get 1.28 times 10 to the -4. Okay, so that's x, that's the molar solubility, so that's moles per liter. Okay, last step, convert it to grams per liter. So again, we have to look up what these molar masses are. So the molar mass of silver, hopefully I can do this a little bit more quickly, is 107.87. Okay, so let's do our molar mass. Just make sure. 107.87. So silver is 107.87. And then you've got a carbonate, so that's carbon. And then you got 3 oxygens. Okay, so let's add them all up together. 107.87 plus 12.01 plus 3 times 16 is 48. So you get 167.88 grams per mole. So there's your molar mass. If we take our value in moles per liter, so 1.28 times 10 to the negative 4 moles per liter, and multiply it by 167.88 grams per mole, that will cancel the moles and we'll get grams per liter. Okay, so our value of X, which is the solubility, okay, so times 1.28 times 10 to the minus 4, and you get 0.021, 2 significant digits, and then that's grams per liter. Let's write these over here. Okay. Now, you could get fancy about this and say, hey, that's a pretty small number, but it's actually, if I moved it over 3 places, I'd get milligrams, right? So you could also say it's 21 milligrams per liter. But the Alex problem usually would just stop at grams per liter. Okay. So the difference between solubility and molar solubility. Solubility is typically the mass that dissolves into a liter of solution. Mass of the solid. Could be the moles, that would be called molar solubility. KSP is related, but KSP is the value of the equilibrium constant associated with the dissolving of that solid into water.